Okay, before we can make sense of the new content that we're going to cover this week, I'm going to take you back to page 7 of your OneNote, which we were working on last term. Now, in one of the Zoom sessions, we went through the calculations that are at the top of page 7, but then at the bottom of page 7, there's an interactivity for you to go to. And if you haven't completed that interactivity yet, you really should do that first. Okay, now on the next screen, I've got the interactivity open, and basically what's involved with this interactivity is that you choose a substance. So in this case, I'm going to choose HCl. You can increase the volume. It really doesn't matter what the volume is. I'm going to go for 100 milliliters, but it really doesn't matter. And then you can also select the concentration. Okay, so if you look at the first row of the table, what you've been asked to do is to work out the pH of a 0.001 moles per liter solution of HCl. Okay. Now, what's a little bit tricky about this interactivity is that they've asked you to enter the concentration as something times 10 to the power of minus 3 or something times 10 to the power of minus 2. So if we want 0.001, the way you actually need to enter that is 1 times 10 to the power of minus 3. Okay. We can see that when we've got a 0.001 moles per liter solution of HCl, the pH is 3, and that makes sense because if you remember, pH is negative log of the hydrogen concentration. Now, if we've got HCl, that's a strong acid, so it's going to dissociate fully into hydrogen ions and chloride ions. And since we've got a concentration of 0.001 moles per liter of HCl, that means that we will also have a concentration of 0.001 moles per liter of H plus ions and 0.001 moles per liter of chloride ions. So the pH is going to be the negative log of 0.001, which turns out to be 3. Okay, so that makes sense. Okay, let's have a look and see what happens if we change the concentration of the acid. Okay, now this time instead of 0.001, I'm going to try 0.01. And again, I'm going to lower the probe. And we can see that the pH is now 2. Now again, this makes sense because this time the concentration is 0.01. Since it's a strong acid, it completely ionizes into hydrogen ions and chloride ions. And so the pH is now going to be the negative log of 0.01, which when we put into a calculator turns out to be 2. Okay, so that's what we would expect. Okay, but what I wanted you to notice is that the concentration has increased by a factor of 10 and the pH has decreased by 1. Okay, now the other thing that you needed to do in trying this activity is to try different acids. Okay, so we can see that if I've got HCl and the concentration is 0.01 moles per liter, the pH is 2. Let's see what happens if instead of choosing HCl, we choose a diprotic acid. Okay, so let's give that a try. Okay, so I've chosen sulfuric acid, which is a diprotic acid. I've used exactly the same concentration, 0.01 moles per liter, and the volume is the same. Not that the volume makes any difference. Okay, so I'm going to insert the probe. And you can see that the pH now is only 1.69 rather than being 2. Okay, let's have a think about what's happened this time. Okay, this time we've got a diprotic acid. Again, it's a strong acid, so it completely ionizes. But this time it's producing 2 lots of H plus ions and 1 lot of sulfate ions. So if the concentration of sulfuric acid is 0.01, the concentration of H plus ions is going to be 0.02 moles per litre, because we're getting 2 lots of H plus ions for each lot of sulfuric acid, and the concentration of sulfate ions is going to be 0.01 moles per litre. So to work out the pH this time, we have to do the negative log of 0.02. And that's why we're getting a different answer. Okay, so that's a strong acid, but it is diprotic, so that's why we're getting a different answer. Okay, now let's try a different acid. This time we might try a weak monoprotic acid. Okay, so I've got a weak acid this time. Same concentration, same volume. I'm going to lower the probe. And what we find is that the pH is significantly higher for a weak acid. Okay, so the reason that this has happened is because it's a weak acid and it's not dissociating fully. Whilst the concentration of the acid might still be 0.01 moles per litre, the concentration of H plus is going to be significantly less than 0.01 per litre. So since the pH is 3.38, we can work out the hydrogen ion concentration. If you remember, the hydrogen ion concentration is going to be 10 to the power of minus pH 0.00042. Okay, and now that we know the hydrogen ion concentration, the percentage ionization is going to be the hydrogen ion concentration divided by the acid concentration times 100. So it's going to be 0.00042 divided by 0.01 times 100, and that works out to be 4.2%. So 4.2% of the molecules of this acid ionize when the concentration is 0.01 moles per litre. Let's find out what happens if we dilute the acid. Okay, I've changed the concentration of the acid. This time it's 1 times 10 to the power of minus 3, so 0.001 this time, and the pH is now 3.9. Okay, so let's go through all of the same calculations and find out what the percentage ionization is now. The pH is now 3.9. The hydrogen ion concentration is going to be 10 to the power of minus 3.9. That works out to be 0.00013. Now to work out the percentage ionization, we follow exactly the same steps as before. So it's going to be 0.00013 divided this time by 0.001, because we've got a new concentration for the acid, and if we put that into a calculator, it works out to be 12.6%. So what we can see is that when the acid is more dilute, the percentage ionization is greater. Okay, now if you continue working through the activity on page 7, you can see I've also asked you to measure the pH of some bases of different concentrations. There are some bases such as sodium hydroxide that ionize to produce one single lot of hydroxide ions. There's a base like calcium hydroxide that produces 2 lots of hydroxide ions for each mole of the base, and there are also some weak bases. But let's just have a quick little look at sodium hydroxide. So I've got some sodium hydroxide here that I've placed in the beaker. The pH is 12. Okay. Now, if we're wanting to work out why the pH is 12, let's keep in mind that pH plus pOH is equal to 14. So if the pH is 12, then pOH must be 14 minus 12, which is 2. Okay. Now, sodium hydroxide, when that dissolves in water, that's going to produce sodium ions and hydroxide ions. So it's a strong base, so it fully dissociates. So if I've got a 0.01 mole per litre solution of sodium hydroxide, it's going to produce a 0.01 moles per litre solution of sodium and also of sodium ions, and also 0.01 moles per litre of hydroxide ions. So if I want to work out the pOH, it's going to be the negative log of 0.01, which works out to be 2, and that's what we worked out in the previous step. So that pH makes sense. Okay, so make sure that you finish working through the activity that's on page 7 before moving on to this week's work.